Welcome back to basic electronics video lectures. Now this is the continuation lecture of first topic PN junction diode. Now here we are going to study the ideal characteristics. Now if you see, this is the ideal characteristics. Diode equivalent symbol, if you take ideal, it acts like a closed switch. So when we apply the just more than zero voltage, then it starts conducting. Now coming to the reverse, when we apply the reverse bias, it acts like an open switch and it will not allow any current. So that's why here you can see there is no drop in the forward bias and there is no minority charge carrier current in the reverse bias. This is about the ideal characteristics. Now in this case, it offers the zero resistance, and in this case, it offers the infinite resistance. But practically, this is the practical VI characteristics. Now in this in the forward bias, it offers some drop. The diode drops some voltage that is called the forward voltage or cutting voltage or knee voltage. And similarly, in the reverse bias, a small current flows, that is because of the minority charge carriers, or we can also call it as a reverse current or leakage current, we can call it. Thereby what here, instead of offering the infinite, some high voltage, high resistance it offers. And here, instead of 0 ohms, it offers some ohms in the order of, below the 100 ohms it will offer. And here in the order of mega ohms are thousands of kilo ohms. Now that we will see. And these characteristics, now this is the current flowing through the diode, we can calculate by using the diode current equation. ID, diode current ID is equal to I naught or IS, saturation current or temperature dependent saturation current, anything. I naught or IS, both we can denote. So ID is equal to I naught into e to the power of VD divided by eta Vt minus 1. This minus 1 is for the e to the power of Vd eta Vt minus 1 here. So this Vd is complete, entire thing is in the exponent. So now where Vt is the thermal voltage or temperature dependent voltage, and Vt is equal to K into capital T divided by Q, where K is the Boltzmann constant, where T is the temperature in Kelvin and Q is the electron charge. And Vt is equal to, we can also write it as capital T divided by 11,600. Now here K value, Boltzmann constant, and Q value, electron charge, after substituting, we are going to get this value. So Vt is the thermal voltage. Now where temperature T is the in the order of Kelvin. And Vd is the diode terminal voltage in the order of volts. Nothing but what? Across the diode, how much voltage is available, that voltage. And I naught is the temperature dependent saturation current. This is the reverse saturation current, we can also see. Reverse saturation current. In the data sheet, this value will be available. And T is the absolute temperature of the PN junction diode in the Kelvin. So at what temperature we are operating the diode, depending upon that, we need to substitute this T. And K is a Boltzmann constant, Q is the electron charge, and eta is a constant, and that is 1 for germanium and 2 for the silicon. And ID is the diode current or current flowing through the diode. This is the diode current equation. Now in this case, now whatever the diode voltage, if you substitute for that, what is the corresponding current value that can be calculated by using this diode current equation. Now coming to the diode resistance. Now there are two types of resistance are offered by the diode, that is a forward resistance and a reverse resistance. If the diode is connected in a forward bias, it offers the forward resistance. If the diode is connected in a reverse bias, it offers the reverse resistance. Again, in the forward resistance, depending upon what supply we have connected, DC supply or AC supply, again, it offers the two types of resistance. One is a static resistance or DC resistance, and dynamic resistance or AC resistance. Now, what is static resistance? The resistance also defined as the ratio of DC voltage applied across the diode to the DC current or direct current flowing through the diode. RF is equal to DC voltage divided by the DC current, because this is the DC resistance denoted by the capital R. Now coming to the dynamic resistance or AC resistance. The dynamic resistance is also defined as the ratio of change in voltage to the change in current. It is denoted by the small RF, change in voltage divided by the change in current. Because this is the AC, so we have to take the difference in the voltage and current. Now coming to the reverse resistance, here also we can calculate static and dynamic, but if you take the static and dynamic also, it will give the same value. That's why in the reverse, we can take only one definition. Reverse voltage to the reverse current is called the ratio of reverse voltage to the reverse current is the reverse resistance. It is in the order of mega ohms. Now coming to the forward voltage, forward resistance, it is in the order of ohms. Hardly it is less than 100 ohms. But coming to the reverse, in the reverse, diode is not allowing any current. So if the current is not flowing, then it offers very high resistance. Now coming to the applications of the diode. Because diode is used as a switch, it helps faster in and on and off for the output that should occur in a quick rate. So basically diode is a switch. And because of this on and off, and it is allowing only current in one direction, we can use this diode for the rectifiers. And this rectifiers topic we will study in the next lecture.